Hey, anybody have any homework questions? Has anybody tried that polar coordinates problem? You get through it? Okay. Oh, in the solutions? Yeah. Yeah, sometimes I do those a different way. Yes, on linkages. Okay. What? Oh, yeah, that's fine. Okay, so that's this one, right? You have a member like this and one like this. Is that right, Lillian? And this angle's 45 degrees. Um, the lengths of each one are 1 meter, and the mass is 5 kilograms. No friction between the wall and the top member, and uh, it's at rest at this instant, so there's no angular velocity for either of these members. And we want to know the acceleration of the pin joint there. So if that's the point C, we want to calculate the acceleration of C. Um, and there's nothing else, no other external loads acting on it except the weight. Um, so let me just, so I'll call that A, I'll call that B, this member 1 and this member 2. Let me do the free body diagrams and then talk about the constraints. And I think I'm not going to go through the whole calculation, but so a free body diagram of member 1. There's a weight force of 49.05 newtons. There's a reaction force RA. And then there's a force vector here on 1 by 2. When you write out Newton's laws, this has a fixed point. So we're not going to use Newton's second law. And that means that the only variable from this, the only variables are going to be F1, 2. And I guess it's only going to be the X component, actually. And then free body diagram for member 2. There's a weight here of 49.05. Here there's a force on 2 by 1, so that's negative F1, 2. And then here there's a contact force. Since that's a frictionless contact, that's just a horizontal force. I'll call that RB. It's just a scalar because we know the direction. And the variables we have, let's see. In our equations, since RA is not going to appear in our equations, we're going to have 4 equations from Newton's laws. And the variables are going to be F1, 2x, alpha 1, the acceleration of the center of mass of 2, alpha 2, and that is 2, 3, 4, 5, 6. What? Yeah. 1, 2, 3. Well, so this is, let's write this as a vector. We'll have an equation for the y component. Will we? It's just going to, oh yeah, for member 2, exactly. Yep. So 1, 2, 3, 4, 5, 6, 7. So we need 3 constraints. And those are going to be that the acceleration at C, according to member 1, is equal to the acceleration at C according to member 2. So that's 2 constraint equations. And then the acceleration at B, X component, is equal to 0 because the edge of that thing has to stay pressed against the wall. And so this is one constraint equation. And so then you can solve it. Any other questions about that one? Any other homework questions? Okay. Well, I'm going to do that example using you guys know what a 20G centrifuge is? It's sort of a technical thing that people like me and astronauts know about. So that's this thing. And we're going to do this calculation 3 ways. So we're going to calculate the acceleration of the astronaut. First, we're going to use a coordinate system that doesn't rotate and it's fixed at the axis. And the orientation I'm going to use is horizontal, Y vertical, Z coming out towards us. Oh, come on. Z coming out this way. So this one, even though it's located at the axis, it's not rotating with the arm. Then I'm going to use one that's mounted to the arm at the axis. And at the instant that we're looking at it, it has the orientation that's shown in that picture. So that means that at this instant, the coordinate system in part two is going to look like that. But in the next instant, when this chair is a little bit that way, that coordinate system is going to be rotated a little bit. So the orientation that it has there only represents this exact instant. And then the third one is going to be the coordinate system mounted to the arm at the midpoint. So that one is going to be here with instantaneously the same orientation. And the accelerations that we calculate in these three ways have to match. We're calculating the astronaut's acceleration as we could use in Newton's laws. So we're going to see how these three, like the different parts of the calculations, are going to come in differently. But in the end, they'll all be the same. So notice that this first one is an inertial coordinate system. That coordinate system, the origin isn't moving, isn't accelerating, and the axes aren't changing orientation. So all we have to do is calculate what it sees the astronaut doing, and that's the true acceleration. The second one, the origin is not accelerating, but the axes are changing orientation. So this is a rotating coordinate system. We're going to have to use our new approach we're talking about right now to calculate number two. The third one, the origin is moving in a circle, so it's accelerating. So the origin is accelerating and the coordinate system is rotating. So we're going to have to deal with both of those two. We're going to have to correct for both of those two problems to get the true acceleration. And the length of the arm, this distance is 5 meters. And I think I used 2 seconds for a full revolution. I want to be careful. I don't want to kill this guy. No, he's glued. No, his stuff is glued to the chair. One revolution every 2 seconds. And then at the end, once we get this acceleration, let's calculate the net force too. Why not? Okay, so the first one is an inertial coordinate system. And all that's happening here is, this is just a circular motion problem. All right, so in that coordinate system, the magnitude of the angular velocity is, so one revolution is 2 pi radians. It's 2 pi radians every 2 seconds. And so that's pi radians per second. And if it's rotating this way, what is that as an angular velocity vector? So positive y. So omega is equal to 0 pi 0. Okay, why is this lowercase omega and not capital omega? What? Yeah, I mean, lowercase omega always represents bodies, how they're moving in the coordinate system. It's an angular velocity of bodies. A capital omega is an angular velocity of a coordinate system. Our coordinate system isn't moving. This is just tracking our coordinate system, tracking this guy, you know? Like, our coordinate system is just, it's a camera and all it sees is the wall. It's just looking at the wall. And then every once in a while, it's like, ah, help me, ah, you know? So um, this doesn't have anything to do with the motion of the coordinates. All right, and now acceleration. So how are we going to calculate the acceleration? It's just circular motion in an inertial coordinate system. I know it's just a lot of stuff. Yeah, watermelon equation. So this is, and we're going to assume this is constant for all of these. So acceleration is equal to alpha cross r plus omega cross quantity omega cross r. And we're assuming constant angular velocity, so that part goes away. Omega is 0 pi 0, and we're crossing that with the quantity 0 pi 0 crossed with the r vector. The r vector goes from the center of the circular motion to the point in question. So what's the r vector here? Yeah, so the center of the circular motion is the origin. And so r is just 5 meters in the negative x direction. So the cross product of the stuff in parentheses is 0, 0, 5 pi. And so the total acceleration of the astronaut is 5 pi squared 0, 0. And so that's a little under 50 meters per second squared. No, yeah, a little, yeah. About 50. What is it? And then if the astronaut has a mass of 100 kilograms, then the net force applied to the astronaut to keep this rotation is 100, it's about 5,000 newtons. And that's mostly provided by the chair. Okay, so now we're going on to the second one. The origin is fixed. The coordinate system is rotating. So we have to figure out, we're going to use this relationship that says the acceleration is equal to the acceleration as observed by the coordinate system plus capital omega dot crossed with the position vector plus 2 times the angular velocity of the coordinate system crossed with the velocity vector as observed in the coordinate system plus capital omega cross quantity capital omega cross p. So let's figure out what these individual parts are, and then we'll put it all together. First of all, position vector in this coordinate system. So now we're talking, the coordinate system is still located here, but it's rotating with the arm. In this instant, what's the position vector? Negative 5, 0, 0. What's the angular velocity of the coordinate system? So now we're talking about a capital omega. Yep, that is the same as what the rotation of the astronaut was in the coordinate system before. That's the same motion. They're all sort of a fixed, rigid body together. And this is not changing, it's constant, so omega dot is 0. And now we have to think about the observed velocity and observed acceleration. So this video camera now is just aimed at the astronaut the whole time. Okay, so it's just looking at this guy writhing around, wondering what his problem is. So what does it see? What does the camera see for the velocity of the astronaut? 0, yep. So V observed is 0. And the same thing for the acceleration. If the velocity function of time, just stays 0, then the observed acceleration also just stays 0. Now we have everything we need to put that into this expression. So the acceleration is equal to 0, 0, 0 plus 0, 0, 0 cross negative 5, 0, 0 plus 2 times 0 pi 0 crossed with 0, 0, 0 plus 0 pi 0 crossed with the quantity 0 pi 0 cross negative 5, 0, 0. This goes away, this goes away, this goes away. And what we're left with now is just that unobserved centripetal acceleration mathematically, that term is the same as the last term of the watermelon equation, but what it means something different here. And so we get 5 pi squared 0, 0. Even though the camera itself now doesn't see any motion at all. Okay, so now we're going to do the deluxe model. So this one, the coordinate system is fixed halfway up the arm. So the origin is moving in a circular motion. And the coordinate system is rotating. Okay, so let's name this point. I guess I'll call this B. Well, how do we deal with these two separate ways that this coordinate system is non-inertial? So it's non-inertial partly because the origin is accelerating and partly because the coordinate system is rotating. The coordinate system rotating, we're going to use this approach, that we're talking about right now, that we used in step 2, part 2. But the origin accelerating, we have to do differently. So what's our strategy for that? Yep. Relative motion. Yep. So the acceleration of the astronaut relative to the ground, that's what we want, is equal to the acceleration of the astronaut relative to that point B, plus the acceleration of the point B relative to the ground. Okay, this is the acceleration of the origin. And this is the acceleration relative to the origin using the rotating coordinate system approach. Okay, so first let's figure out the acceleration of the origin. So the acceleration of B relative to the ground. How are we going to figure that out? Well, we've been doing problems like this like all semester. That's just circular motion. Okay, so this is just going to be alpha cross R plus omega cross quantity omega cross R. This term goes away because the body that we're talking about is like the arm. It doesn't have any angular acceleration. And so this is just equal to 0 pi 0 crossed with the quantity 0 pi 0 cross R. R goes from the, now remember the difference between R and P. P goes from the origin to the point you care about. R goes from the center of the circular motion wherever that is to the point you care about. So what's the r vector from the center of the circular motion to, in this case, the origin, to that point B? Negative 2.500. Any questions about that? And so the acceleration comes out to be, this is just the acceleration of the origin, and it's equal to 2.5 I squared zero zero. And now we're going to calculate the acceleration of the astronaut relative to B. So now we're going to assume that that point B is fixed in space. It's still, the coordinate system is still rotating. Any questions about that? Okay, so the acceleration of A is equal to the observed acceleration of A plus capital omega dot crossed with the position vector plus 2 times capital omega crossed with the observed velocity vector of the astronaut plus capital omega cross quantity capital omega cross P. All right. So first, what's the position vector? Our origin is at B. Okay. So what's the position of the astronaut according to our coordinate system? Negative 2.500. The coordinate system is rotating. What's the angular velocity of the coordinate system? It's still 0, pi 0. Yep. Where it is doesn't matter. The only thing, so we don't care about the fact that the coordinate system is moving in a big circle now for this calculation. We only care about how long it takes, for it to return to its original orientation. Okay. So the way we're thinking about it now, that coordinate system is just sitting in place and just changing its orientation. And it's changing its orientation the same speed it is if you consider it moving in a big circle. It still takes 2 seconds for it to get back to looking at the same thing it was in the first place. Okay. It's a constant angular acceleration, so capital omega dot is 0. What about the observed velocity of the astronaut according to that coordinate system? 0. And same with the acceleration, right? The astronaut is only half as far away, but the camera still just sees the astronaut sitting in place. So the observed velocity is 0, and the observed acceleration is 0. And so put this all together, the acceleration of A relative to B is equal to 0, 0, 0 plus 0, 0, 0 crossed with the position vector plus 2 times 0 pi 0 crossed with the observed velocity vector 0, 0, 0 plus capital omega 0 pi 0 crossed with the quantity 0 pi 0 crossed with the position vector negative 2.500. Um, so for this one, you get 2.5 pi squared 0, 0. All the other terms go away. And so now we'll put it all together, and the acceleration of A relative to the ground is equal to the acceleration of A relative to B plus the acceleration of B relative to the ground, and that's 2.5 pi squared 0, 0 plus what we got in the first part of this before we went into the circular motion, 2.5 pi squared 0, 0. That's the acceleration of the origin. And you get the same thing again, 5 pi squared 0, 0. Yeah, right. It doesn't matter where you put it. All that would happen is the part of the true acceleration that came from the acceleration of the origin would change, would be bigger as you got farther towards the astronaut and smaller as you got closer. If you put your origin on the astronaut, um, then the acceleration of the origin would be this, and the acceleration of the astronaut relative to the origin would be 0. Notice you could do this. Any other questions about this problem? If you've ever wondered uh, how bad, yes. Yes. So we are always going to do it. We're always going to think of um, so there's always this sort of implied inertial coordinate system. And we'll just always think of that as instantaneously having the same orientation as our rotating coordinate system. But at the next instant, they wouldn't agree anymore, you know? And so if you wanted to track this over time, you can maybe see how, so when they're perfectly aligned with each other, you don't have to worry about anything else. But at the next instant, if we kept the same coordinate systems, our fixed inertial coordinate system would be out of alignment with the rotating one. And we'd have to use a rotation matrix to represent this acceleration in our inertial coordinate system. Okay, so here's a question. Have you ever wondered how far off our acceleration calculations are using a coordinate system that's fixed to the surface of the Earth? You know, the Earth is, I don't know what Canada looks like up there. Oh man, I'm making myself look like an idiot now. I'm just gonna try to draw the world for the rest of class. Okay, and goes off and does some stuff over there. Good enough. Okay, so the world is rotating. I guess we could, which way is it rotating? It rises in the east, so it's rotating this way. Okay. And so when we do experiments in a physics class or whatever, we calculate our accelerations using a video camera or a coordinate system that's fixed to the surface of the Earth. And so, like, if this is our coordinate system, here's us. And if we assume that the center of the Earth is fixed, I mean, that's another issue that you could calculate after this, but let's just worry about the rotation of the Earth first. Is the origin accelerating? Yeah, because of the radius of the Earth. We're not at the center of the Earth. We're out at the so the origin is accelerating. And the coordinate system is rotating. So we'd have to deal with both of those two things. And basically, so the question is, how different are the accelerations we calculate? Well, sorry, those aren't the accelerations we calculate. How different are the true accelerations compared to an inertial coordinate system and the observed acceleration that we measure? You know, that's the question. They're not very different. The reason for that is, so with this thing, we were doing a revolution every 2 seconds. How often does the Earth do a revolution? That's the whole time around. I'm just talking about the thing spinning. So 1 day, but that's still a lot more than 2 seconds, you know. So we do, excuse me, 1 revolution every 24 hours. So that's 2 pi radians every 86,400 seconds, I think. Can someone tell me what that number is in scientific notation? (8.64 times 10 to the what? Minus fourth? Okay. 7.27 times 10 to the minus 5 radians per second. Okay. But we do have a big R value and a big P value because the radius is, I forget what it is, it's like 10 times 10 to the 6 meters. But you can do all this and calculate the difference between those two things. I think you should do it. I think you won't want to start, but once you start, you'll be happy. The answer is, I mean, as we know, so like when we do calculations in Physics 1 lab, we always assume that our coordinate system is inertial. And it's not because of this problem, but it's pretty close. And when you're doing experiments that aren't that sensitive, you know, I basically your experiments have to be very, very sensitive in order to notice this difference. Yeah, that would be the next step. And then you got to do the rotating of the sun about whatever it rotates about. Yeah. What? No, it's totally different than that. Um, this is this is irrespective of gravity. Okay, that's all.